This lesson is going to be about Newton's third law, and the learning target is to be able to describe how objects act in collisions using action-reaction pairs. So we're going to be looking at both what are the forces acting on these objects, and then how are those objects affected by those forces. So we know that as we're looking at the forces acting on an object, if something is on Earth, if you are standing on Earth, we know that the force of gravity is acting on you, pulling you downwards towards the Earth. We ask ourselves that question. If it's yes, we can say that the force of gravity is pulling us down towards the Earth. We all know this because Earth is so massive that it has its own gravitational pull, pulls us down towards it. But what if I told you that you actually pull the Earth towards you with the same force of gravity that it pulls you downward towards the Earth with? Would you believe me? So in order to figure out why this is true, we're going to have to look deep into space through our telescope where we find an astronaut working on a satellite. So this guy is out here trying to do a little maintenance. And when he gets to the edge of this satellite, for whatever reason, he's trying to push this thing into a different position. And so this guy gives it a little push. And what happens is, if we think about what's going to go on in space here, this guy gives it a little push and the satellite starts to take off this way. Well, the astronaut doesn't just sit here. When he pushes that thing, they both spread apart from each other. Right? They kind of float there, going outward like this. And so when we look at both of these objects, right, the astronaut gave a push onto the satellite, right, which caused the satellite to accelerate. We can see that if the satellite starts to move in that direction, it's accelerating, so therefore there was a force acting on it. But if the astronaut is accelerating in the rightwards direction, that means there must have also been a force on him. Remember, because forces cause acceleration. So if we see an acceleration, there must have been a force. And so we know that there was a force acting backwards onto the astronaut. And this force was actually the paired force, the reaction pair of the force that the astronaut put onto the satellite. The first one would be called the action force, and the second one would be called the reaction force, because these forces happen in pairs. Every time that we have a force, we have an equal and opposite reaction. You've probably heard that before. It's actually Newton's third law. And so we look off into our space through our telescope, and we see another spaceship. And what we get here is you think about it, how does a spaceship work out in space? Well, there's no air out in space, and so what's pushing the spaceship forward? And so we think, well, of course, the gases. This thing shoots a bunch of gases out the back, and so that's what pushes the spaceship forward. But if you look about at the force arrow here, well, the spaceship is pushing gas backwards through it. So why does that make the spaceship shoot out in this direction? That doesn't make any sense at all. Well, the reason is because the force that pushes the gas out the back of the spaceship, that force that's applied onto the gas actually causes the gas to apply an equal and opposite force on the spaceship. And so what we get is we get our action of the spaceship pushing gas out the back of it, and we get our reaction of the gas pushing back on the spaceship, causing it to move forward. Now we don't see the gas quite as much as we see the spaceship, but we can see that the space shuttle is definitely accelerating forward. So we know that this force is happening, and this is another example of the action-reaction pairs that happen because of Newton's third law. So if we're going to describe this, you've heard this before, that for every action there's an equal and opposite reaction. So for every force, there's an equal and opposite reaction force on the other object. And so if I was going to, let's say we look at the skaters here. Let's zoom in on these guys right here. So we've got two skaters. Let's call one, and let's call one, two. And so if we're going to draw force diagrams for these two skaters, well, what's going to happen? They're both pushing on each other. And so I know that this skater one is going to push this direction onto skater 2, and skater 2 is going to push in this direction onto skater 1. And so if I was going to draw force diagrams for these two skaters, let's say this one is 1 and this one is 2, I know that for skater number 1, there's going to be a force in this direction, and I'm going to call it 2 on 1, the force from skater 2 onto skater 1. And if I was going to draw the force diagram of skater 2, I would draw a force in this direction, and this would be the force of skater 1 onto skater 2. And so you can see that my two forces on each of these objects is equal, they are opposite, and the important part here is they're acting on different objects. We don't have two forces that are equal and opposite acting on one of the skaters. We have two separate forces acting that are equal and opposite on each object, right? And you can look at the notation. We have 2 on 1 and 1 on 2. It's flipped. In the first action force, 2 is acting onto 1, and in the reaction force, object 1 is acting on skater 2. And so if we looked at this one right here, we have a swimmer, right? We have the swimmer is enacting a force of the feet onto the wall. The skater is actually pushing onto the wall, and therefore the wall pushes out onto the feet, which propels that person forward, and that's where their acceleration. And we can see that this force is happening because we can see that there's an acceleration to the left. And so if I was going to draw a force diagram of the swimmer, I would draw this right here, and I would say I'm just going to go W on F, wall on feet. But if I was going to draw, let's say I was going to draw a force diagram of the wall now, I would have a force in the opposite direction of the feet on the wall. And so I would have, with this force diagram of the swimmer, I could draw a lot of different forces on here. I could draw, maybe there'd be a little friction force, force of friction from maybe the water. I could draw the force of gravity acting onto them, right? There's all these different forces, but throughout all of these forces, this force of W on F and this force of F on W is my action-reaction pair because they're equal, they are opposite, and they're acting on different objects. And so that would be my action-reaction pair, which causes the swimmer to accelerate. And it would be the same type of idea here with the boat. And so if I had someone stepping off of a boat, I have the action of the person stepping off, so which that would be actually that would make the person go forward. It'd be the force of the boat on the person, and we'd have the force of the person on the boat, which caused them to go backwards. But it'd be the same type of ideal action reaction. We can see this happening because they both accelerate in different directions. And so things to remember with your action reaction pairs is that they're equal, they are opposite, and they act on different objects. And so we got to look at this question of why are some objects more affected than others? Because I said at the start that I pull on the earth with the same force that the earth pulls on me, but I am definitely more affected by the earth's gravity than the earth is by mine. And so we can really label this as cause and effect because the effect that we are seeing when we think about effects, we're talking about acceleration, right? Because I know that I accelerate down towards the earth, and the earth doesn't necessarily accelerate up on me. The cause of that acceleration is the force, right? We are exerting the same force onto each other. And so if we have the same exact equal force exerting onto each other, but we see different accelerations, then we got to figure out what is the mechanism here? What's the cause of that difference? And it's really the difference in mass, right? Because if we know that acceleration equals force divided by mass. And so if you have the Earth here, which is very massive, right? It has a ton of mass. And you have little old me, which is not very massive. I'm going to just go low mass. Well, which one of us is going to be accelerating more from that same amount of force? Well, if we look at this mass, this equation right here, mass is on the bottom. And so if we have a really, really big mass, that's going to make the acceleration very, very, very small. Right? If we have a small mass, we're going to have a really big acceleration. Remember the concept of inertia. The Earth has much more inertia than I do, and so the Earth is much less affected than of the force acting on it than I am. And so we actually draw out this example of me standing on top of the Earth while I'm standing on here with my messed up leg, and I'm being pulled down by a force of the earth on me, and I'm having the same effect onto the earth. I am pulling me on earth. I have the same force of gravity that the earth has on me, except for because the earth has much more inertia and it's much more massive, it is not affected as much as I am by that interaction. And so we have the same thing over here with the moon and the earth. If I have the force of the earth on the moon, that is the same magnitude of force in opposite directions of the moon on Earth. And we can actually see how this works because we know that the moon orbits around the Earth. Right? Well, the Earth is definitely having an effect on the moon, causing it to accelerate around and around. The moon has some effect on the Earth, and so we can tell that this force is happening. We can see that, like the tides come and all the water will pull towards this side. What it actually does is the moon actually pulls the water on the Earth towards it. So that's why high tide happens right here, and you get low tide over in these spots because what you end up getting is something that looks a little bit like this happening with all of the water around the earth. And so you get high tides at these points and you get low tides over here on the edges. And so we know that the moon has an effect on the earth. It is the same exact force, but because of the difference in mass, there's a different effect that we see. There's a different type of a different amount of acceleration for both those objects. And so whenever you see a force, you need to think about the reaction force that is caused by that force, that action force. And so I hope that this helps you to be able to describe how forces act in collisions and how that changes the motion of objects in collisions using Newton's third law.